We have an example of a linear factorization theorem. Suppose the factors of a third degree polynomial are 2 and a I, where this is a complex number and this is a real number. Obtain the function if f of 1 equal to 15. Let's have solution this way. Solution. Now, the polynomial is of degree 3. Which is equal to, from linear factorization theorem, we can have it to look like A, which is the constant, then the possible zeros will be here. For this case, let's say, because it is a third degree polynomial, we have 3 factors. Let's say the first factor is s equal to p, then s equal to q, and then s equal to r. All these factors. Now we need zeros, so that x minus p equal to 0, the first one, then s minus q equal to 0, another one, then x minus r equal to another 0. Okay, so we can insert all the zeros here and multiply them out. X minus p is the first 0, then x minus q now, then s minus r. Okay, so given from the question that the first factor is 2, we can have this to be equal to a. Let's relate this to the first factor, which is 2. Then the second factor is I, right? S minus I. Then what will be the third factor, which is r, right? Now, remember from linear factorization theorem, we have another theorem called the complex conjugate theorem, which states that whenever a complex number, as this case, I, is one of the factors of a polynomial, then the conjugate of that complex number, which is minus I, must always be a factor as well. So that our third factor now will be minus I. So if we insert minus I here, we have positive I. Okay? So that this will look like A x minus 2. Let's start the multiplication from this side. So this x will go for this s, we have s squared, right? And this and I plus xi, this and this, we have minus xi, right? And this as minus I squared. Okay, so that obviously this and this will cancel out. We can be left with a bracket s minus 2 this way, then s squared. What is I squared? Recall that I itself equal to square root of minus 1, right? So what if you decide to square both sides of the equation? We have I squared equal to root minus 1 all squared. So these two will cancel the root. So we'll be left with minus 1, right? So we can insert minus 1 here, so that this negative and negative 1, this we already have negative here, that's it here. The negative 1 is coming, so that it will change it to positive 1 this way. Then you can still expand further. That is a, this will go for this, we have s cubed, right? Then this will go for this plus x minus 2 and s, that's minus 2s squared, then minus 2 and 1, that's minus 2, right? Okay, now recall from the question that f of, okay, let's write this first. F of x now will now be equal to a, that's s cubed, plus x, then minus 2x squared minus 2, right? Okay, in that case, we are given from the question that f of 1 equal to 15. That means wherever you see x, just insert 1 so that we'll be able to know the value of this a here. So f of 1 equal to 15, then equal to a, that's 1 cube plus 1, then minus 2, 1 squared, that's minus 2. So we have it to look like 15 equal to a, that means this and this will give you 2, minus 2, minus 2. So let this cancel this. We'll be left with minus 2. That means 15 equal to minus 2a, right? That means a equal to 15 divided by 2, all negative. So we can return this a here. F of x will now look like minus 15 over 2, the value for a. Then we can have s cubed. When we rearrange, we can have minus 2s squared minus 2s squared, then plus x, and then finally minus 2. You can leave it this way, and if you like, you can expand further to give f of x equal to this, multiply this, we have minus 15s cubed divided by 2. Negative and negative, we have positive 15s squared, because these 2 will cancel these 2. Then we have plus, okay, because of this negative, we have minus 15 over 2, that is x. Then finally, this negative and this negative, we have a positive 15. These two will cancel this, and this is the final answer. Thank you very much.